All right, so we have seen that if a function does, which has the derivatives of all order at the center of convergence, then if it has a power series expansion, then it will have to look like that. an, where an is the nth derivative evaluated at c divided by n factorial, times the corresponding power of x minus c. Well, does it converge though? And does it converge to f of x? In other words, is what we expect to happen in fact what does happen? And in fact, it is. So if we have a function that has all derivatives at x equals c, it turns out that the Taylor series, which is exactly what we have constructed, so the sum from 0 to infinity of the nth derivative at c divided by n factorial times x minus c to the power n, does converge to the function over its interval of convergence. And of course here the its refers to the series, not the function, because the series, power series have intervals of convergence, functions have domain. So this is what a Taylor series is. It's a way of constructing the power series for a function, but just knowing the function without having to rely on special formulae. Now, of course, the construction of this generic formula will work in a humanly reasonable way as long as those derivatives have some kind of pattern that can be written easily as a formula. If those derivatives turn out to be all over the place, then it becomes difficult to do. But at least theoretically, we can do it. Now, there is a special case of a Taylor series, and that's a situation where the center of convergence is actually the value 0. And when that happens, so when we're computing a Taylor series centered at 0, which of course is the easiest number that we have, the one that we keep looking at most often, then we're calling this the Maclaurin series. So Maclaurin series is something of the form sum from 0 to infinity of the nth derivative at 0 divided by n factorial times simply x to the power n. And again, the main advantage of these series is that they actually look like very simple power series. The center is 0, the formula simplifies and so on, but there's nothing special about Maclaurin series. They're just a special kind of Taylor series, a very particular kind. Now that we have a Taylor series for a function, what we can do is we can look at how to use it to approximate the function. And it is the following. Once I have the Taylor series, what I can do is I can actually restrict my attention to just the sum of the first k terms, so the kth partial sum of the Taylor series. And because this is now a true polynomial, because it's finite, it's not infinite, we're going to call this the kth Taylor polynomial of f of x. So this will look like the sum from 0 to k of the nth derivative of evaluated at c divided by n factorial, etc., etc. Okay? And so this will look like this. So we'll have bf of c plus f prime of c times x minus c plus f double prime of c divided by 2 times x minus c squared, etc., 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 up to the kth derivative evaluated at c divided by k factorial times x minus c to the power k. So what are these polynomials good for? Well, they provide a reasonable approximation to f of x. So they allow us to have a formula that can be worked out even by hand if you have the patience. And as long as you know the formula for all those derivatives, but they allow you to compute the function in these particular situations. Now, of course, you might say, wait a minute, if I'm actually able to compute all derivatives, then what's the point? Now, remember, what we're doing is we're trying to use the series to approximate the function at values other than c. So what we're going to be doing is we're using this approximation for to evaluate the function for values of x near c. Okay? How near? Well, this is the same problem that we have had in other situations. Whenever you're doing an approximation that works near a point, how far we can go depends on how many terms we've used and all kinds of other properties of the function. Okay? So generally speaking, the concept is we can try and approximate the function close to that value. How far away, we cannot tell in general. So in class, we're going to be looking at a few examples of how this is done and how good this approximation gets for successively larger polynomials. And we're also going to have a look at refreshing our mind about what these polynomials actually mean geometrically.